In Unit 3, Homework 1, we're looking at rational expressions. So to get started, let's go ahead and define a rational expression, and then we'll also talk about some domain restrictions that we need to thinking about with rational expressions. So a rational expression is basically an expression that has a numerator and a denominator. Now the thing that we need to be careful of with the rational expression is the denominator cannot equal 0. That's called our restriction. So denominator cannot ever equal 0. So we always have to keep that in mind when we're working with a rational expression, and especially toward the end of this section when we get to working with rational equations. So a rational expression is defined for the entire set of real numbers. That's called its domain. So let's go ahead and look at an example that you'll see in my math lab where it asks you to define a rational expression. So for a rational expression, the set of all real numbers for which the rational expression is defined is called the domain. That means the values that I can input into the function that do not make it undefined. One must exclude the numbers from the set that make the denominator of the rational expression 0. Those are the numbers that we need to look out for. So again, here's our 0 value up here. Now when we're talking about rational expressions, we can add, subtract, multiply, and divide. So let's go ahead and look at adding and subtracting rational expressions. The thing that we need to make sure of here when we add or subtract rational expressions is that we have a common denominator. That means both the denominators have to be the same before I can add or subtract them. Now when we multiply rational expressions, it's pretty easy. We just go ahead and multiply straight across. No common denominator needed. So no common denominator needed. We just multiply straight across. Numerator times numerator, denominator times denominator. Now one thing that you do need to be careful of is you always reduce when you're done multiplying, or you can reduce before you multiply as well. So one way that we could look at this is something like if we had an A over B times C over D, I would multiply straight across A times C over B times D. Now when we divide rational expressions, there's one step I need to take, and then the rules are the same as they were for multiplication. So when I divide rational expressions, we multiply by the reciprocal of the second number. So you multiply by the reciprocal of the second fraction. Now we'll look at to see what this is if we had something like A over B divided by C over D. So A over B stays, and then I switch this to multiplication. The division switches to multiplication, and I multiply by the reciprocal of the second number. Now reciprocal means to flip C over D, and I would get D over C, and then I'd multiply as usual. So I'd have A times D is AD, B times C is BC. So that is how we add, subtract, multiply, and divide rational expressions. Now again, simplification comes into play here, so when we're simplifying, I can simplify first, mean cancel first before I multiply, and then when I get to my final answer, double check one more time to make sure it can't be reduced any further, or I can multiply first and then reduce at the end. It doesn't matter. So be very careful when you're working with these. Make sure you follow these basic directions, and you should be good to go. Let's go ahead and look at some examples of talking about the domain and its restrictions. So for an expression, let's say like x over x plus 3, we might be given something like find all numbers for which the rational expression is undefined. So what we really care about here is where the denominator equals 0. So we think the denominator cannot equal 0. That's what I always have to keep in mind. Well, the denominator for this case is x plus 3. So I get x plus 3 cannot equal 0. So I'd subtract 3 from both sides. This would cancel. And basically I get x cannot equal negative 3. That's my domain restriction. So in an example that you'll run into in my math lab, it'll say type the values for which the rational expression is undefined. So I would have to say the rational expression is undefined for x equal negative 3. So I don't say not equal to because I've already said undefined for this case. So the rational expression is undefined for the value where x is equal to negative 3. Now it could be the case that the rational expression is defined for all real numbers. So I could have an expression, let's say like x over x squared plus 1. And again, I'd start with this, my denominator cannot equal 0. My denominator is x squared plus 1 cannot equal 0. You go ahead and subtract 1 from both sides, and I get x squared cannot equal negative 1. Well, if I'm trying to solve for x, I'd take the square root of both sides here, and right now I'm in the complex number system because I'm trying to take the square root of a negative number. So I get x cannot equal plus or minus the square root of negative 1. And the square root of negative 1 is I. Well, this is a complex number. We're working with real numbers, meaning I can't take the square root of negative values. So for this case, I'd have to say my domain is defined for all real numbers. So here I'd have to say the rational expression is defined for all real numbers. And again, real numbers. Complex numbers I do have a problem with, but we're working in the real number system. So I need to keep that in mind. Now sometimes I can be given a quadratic in my expression. I could have something, let's say like x minus 2 over x squared plus 5x plus 6. Okay, so I still have the same case. The denominator cannot equal 0. So my denominator is x squared plus 5x plus 6 cannot equal 0. Again, I hope that this factors. If not, I'll have to use a quadratic formula. And this does factor into x plus 2 times x plus 3. So here I have x plus 2 cannot equal 0, or x plus 3 cannot equal 0. In this case, I'd subtract the 2 from both sides. X cannot equal negative 2. Subtract 3 from both sides. And I have x cannot equal negative 3. So here, I have to look at the values for which the rational expression is undefined as these two numbers. So the rational expression is undefined for negative 3 and negative 2. So up here, the rational expression is undefined for x equal negative 3. Down here, same thing, we have two values, so negative 3 and negative 2. So you have to kind of keep your eye out for those values where it's undefined. Now a lot of times you're asked to simplify a rational expression. Now the problem that we were just looking at, I couldn't simplify it. Let's go ahead and look at an example where it might be possible to simplify the rational expression. And then after we simplify it, we'll also talk about domain restrictions. So let's go ahead and simplify the rational expression. And when I get all done, we want to talk about numbers to exclude from the domain. Now one thing that we need to be careful of when we're thinking about simplifying an expression there's no equal sign. I'm not trying to solve for x. I don't want like x equals 7 or x equals 2/3. I'm just trying to simplify an expression. And again, there's no equal sign in terms of trying to solve. I'm just trying to simplify, not solve. So let's look at the expression 5x minus 10 all over x squared minus 4x plus 4. Okay, so let's go ahead and get started. First of all, when I'm trying to simplify, I want to try and factor as much as possible, and then hopefully something that I factor will eventually cancel. So in the numerator, I can factor out of 5. I'll have 5 times the quantity x minus 2. Now in the denominator, x squared minus 4x plus 4 factors into x minus 2x minus 2. Now right here is where I want to talk about my domain. The domain would be the denominator cannot equal 0. Now I want to do this before I start canceling. So I do this before canceling. So I have x minus 2 times x minus 2 cannot equal 0. I'd add 2 to both sides. X equal 2. And if you look carefully here, I get the same root both times. So I get x cannot equal 2. So this is my restriction. X cannot equal negative 2, or sorry, x cannot equal 2 is my restriction. So this is my part B to this problem. And then the first part to this problem, I can cancel the x minus 2's. X minus 2 over x minus 2 is 1. So in the numerator, I'm just left with 5 over the quantity x minus 2. So this is the simplified form. So the deal is when you're trying to find your restrictions, you have to do the restrictions before you start doing the canceling. Let's go ahead and look at another example. For this one, we're asked to multiply, simplify. We're not asked to solve, so multiply, simplify, and then we're going to have to talk about domain restrictions at the end as well. Now remember, when we're talking about domain restrictions, these are determined before simplifying. And this is an important lecture quiz question. So domain restrictions are determined before simplifying. So keep that in mind. So for this example, we'll have x squared minus 9 all over x squared times the quantity x squared minus 3x over the trinomial x squared plus 6x minus 27. You know, remember with multiplying, I can multiply straight across, but we don't want to multiply straight across because I'd have a binomial times a binomial and a monomial times this trinomial. What we want to do is factor first. So x squared minus 9 is x plus 3, x minus 3. Now this x squared minus 3x doesn't factor in terms of a product of binomials, but I can pull out a monomial. So I'd factor out an x times x minus 3. Now for my denominator, I still have this x squared. And if we want to, we could think about that as x times x. Now this x squared plus 6x minus 27 factors as well into a product of binomials. So I think we'd call this 9 times 3 is 27. So let's call this a plus 9 and a minus 3. Now this is my simplified version. And because it's my simplified version, this is where I determine what my domain restrictions are. So remember, the denominator cannot equal 0. So our denominator in this case is x times x plus 9 times x minus 3 cannot equal 0. So what we're going to do then is we set each of these pieces equal to 0, each of these factors equal to 0. So I get x cannot equal 0 from here, x cannot equal 0 from here, so it's the same restriction but what we're going to do here is we're just going to make sure we mention them all. Then we have x plus 9 cannot equal 0, and x minus 3 cannot equal 0. Now these are both already solved for. They're the same restriction. So we'd subtract 9 from both sides, and you get x cannot equal negative 9. We'll add 3 to both sides, and I get x cannot equal 3. So I have 4 restrictions here. 2 of them are the same. So for my restrictions, and I like to list these in order from smallest to largest, I say x cannot equal negative 9, x cannot equal 0, x cannot equal 3. So those are my restrictions. Now, we haven't finished the problem yet. That's actually part 2 of this problem, because we always have to determine the restrictions before we simplify. So up here in my expression where I was simplifying, let's go ahead and take this and now come down here and start canceling to find the simplified version. So when we start canceling, we can see that we have an x minus 3 that cancels. One of the x cancels with one of the x down here, and I think that that's all that cancels. So our simplified version would be x plus 3, x minus 3, all over x times x plus 9. Now we do not want to multiply this out. We don't want to distribute the x. This is our simplified version, and this is what we would put into my math lab then. So simplified version, domain restrictions. So those are the things that we want to keep in mind. Now one more time, domain restrictions are determined before you simplify. For instance, if I tried to find my domain restrictions now, there'd be 0 and negative 9. I'd be missing out on this x cannot equal 3. So again, you have to find the domain restrictions before you simplify. Let's go ahead and look at a division problem next. So for this division problem, we have x squared minus 25 over 3x minus 3 divided by x squared plus 10x plus 25 all over x squared plus 4x minus 5. Now our rules for finding the restrictions here are going to be a little bit more complicated because I'm using division. So the first thing we want to do here is factor. X squared minus 25 factors into x plus 5x minus 5. 3x minus 3, the greatest common factor is 3 times the quantity x minus 1. I'm going to leave the division sign in here for now. We'll do our simplification in our next step. X squared plus 10x plus 25 factors into x plus 5x plus 5. And then x squared plus 4x minus 5 factors into x plus 5 x minus 1. So I have a lot of different restrictions that I need to keep in mind here. So remember, the denominator cannot equal 0. So I have a 3 and x minus 1, and then I also have an x plus 5 and an x minus 1 that cannot equal 0. And I guess they're really not actually even multiplied together. If we wanted to think about these separately, I could think about this as 3 times the quantity x minus 1 cannot equal 0. And then I also have another restriction, x plus 5 times x minus 1 cannot equal 0. I'm not going to really worry about those restrictions right now. What I really want to think about now is multiplying. So remember, when you divide by a fraction, you multiply by the reciprocal. So this division changes to multiplication, and then I reciprocate or flip the fraction. So I'll have x plus 5, x minus 1, all over x plus 5 times x plus 5. Now I have more restrictions that I need to keep track of. I still have the 3 times x minus 1 that cannot equal 0, and then I also have another one from here now that x plus 5 times x plus 5 cannot equal 0. So I have to, when I'm dividing rational expressions, I need to factor first, and once I factor, the next thing I would do is talk about the domain restrictions before I flip, and then I'll talk about the domain restrictions after I flip as well. So from here I can see some things will cancel. I have x plus 5 over x plus 5 is 1. I have an x plus 5 over x plus 5 is 1, and then the x minus 1s will cancel as well. So let's see what we're left with. In the numerator it looks like I have an x minus 5. In the denominator I have over 3. This is my simplified expression. So this is one of my solutions. Now my second part to this solution are my domain restrictions. So if you want to think about this, what numbers need to be excluded? We're talking about domain restrictions there. So for here, x cannot equal, in this case I would get a 1. In this case I'd get a negative 5. This case would give me a 1, which is a repeat, and then both of these give me negative 5 and negative 5. Now a lot of these are the same value, and so what I do is I go through and I list them in order from smallest to largest for my domain restrictions. So again, for division, I have two spots I need to find domain restrictions. I have to factor first, and this is before I flip or before I reciprocate, and then after I reciprocate I need to find them. Now when we're asked to add and subtract rational expressions, remember you need to have that common denominator. If you're not given a common denominator, you need to find one. So let's go ahead and look at a couple of examples here. For our first one, let's go ahead and look at adding. Actually, for this one, let's go ahead and subtract. But I'm going to be subtracting common denominators. So I don't have to worry about a common denominator here because I already have one. Now this one's a bit of a trick because I need to make sure that this negative distributes to everything after it. So if I had to rewrite this, this would be x squared plus 4x, and then this minus sign would distribute here to a minus x squared, and then the minus sign would distribute us here as well. Minus a negative 12 is the same as a positive 12. And this is all over x squared plus x minus 6. Next thing we would do is combine like terms. X squared minus x squared is 0, so I'm left with 4x plus 12. And then x squared plus x minus 6 factors into x plus 3, x minus 2. Okay, now remember our job here is to simplify completely. Now before I start canceling though, I need to find my domain restrictions. So again, the denominator cannot equal 0. And our denominator in this case, again, I do this before I start factoring. So x plus 3 times x minus 2 cannot equal 0. So I have x plus 3 cannot equal 0, or x minus 2 cannot equal 0. So for this case, x cannot equal negative 3. For this case, x cannot equal 2. So those are my domain restrictions. And then I need to come over here and finish simplifying. The x plus 3's cancel, and I'm left with 4 over the quantity x minus 2. So this is my simplified form. And this x cannot equal negative 3, 2 are my exclusions. This is my domain restriction, this is my exclusion. So here I was lucky because I already had a common denominator. Now for our next example, we'll be looking at combining rational expressions by addition where I don't have a common denominator. And we'll see what the difference is. Okay, so to get started, we don't need a common denominator. Or sorry, we don't have a common denominator. We need a common denominator. So what we'll want to do is to factor and then kind of compare what we already have, and then based on what we already have, we'll try and come up with that common denominator. Now 81 is a perfect square and so is 16. This is called the difference of perfect squares. This factors into 9x plus 4 times 9x minus 4. Of course the 9x in the numerator doesn't have much to do with it. Now my common denominator here will be 9x plus 4 times 9x minus 4. I already have the 9x plus 4 here, so I need to multiply top and bottom by 9x minus 4. So what we have then is 7 times the quantity, 9x minus 4, plus 9x, and that comes from 7 times the quantity, 9x minus 4, plus 9x, and this is all over 9x plus 4 times 9x minus 4. Now one thing I don't want you to do is you can't cancel the 9x minus 4's because there's no 9x minus 4 over here. What we need to do next is to distribute and combine like terms. I can't do any canceling until I've already determined the domain restrictions. So 7 times 9x, 9 times 7 is 63x, 7 times 4 is 28, 9x plus 4, 9x minus 4. And again, we continue to combine like terms. So I have 63x plus 9x would be 72x minus 28 over 9x plus 4, 9x minus 4. And it looks like to me that both of these are divisible by 2 for sure, even 4. So I could factor a 4 out. If I factor a 4 out, I'm left with 18x minus 7. And then 9x plus 4, 9x minus 4 in the denominator. Now this will not factor any further. This is my simplified form. Nothing will cancel. But remember, we need to find our restrictions here. To find our restrictions, the denominator cannot equal 0. So I would say 9x plus 4 times the quantity 9x minus 4 cannot equal 0. I would take each of these we'd subtract 4 from both sides, divide through by 9, and I get x cannot equal negative 4/9. Here I'd add 4 to both sides, divide both sides through by 9, x cannot equal positive 4/9. So these are my restrictions. If I get solutions that are equal to negative 4/9 or 4/9, then that would mean the fraction would be undefined. So I have to be really careful when I'm working with these. So everything that we've done so far has dealt with a rational expression. Now we're going to start to work with equations. There's a big shift here because now we're trying to solve equations. Now all the problems I did before were called expressions because there was no equal sign in the original problem. Here I have equal signs and I'm trying to solve. I'm trying to find that value of x. Now when we talk about solving an equation, we need to make sure that we never violate any of the domain restrictions that we just were finding up above. So we have quite a few different types of solutions that we can get here. So to start with, we'd have to say an equation that is true for all values of x is called an identity. An example of this, of an identity, would be something like, let's say 3x plus 2 is equal to 2x plus x plus 3 minus 1. Now if we look at this, on the left hand side I have 3x plus 2. On the right hand side, if I simplify this, I'd have a 3x plus 2 as well. So no matter what value of x I plug in here, it will be a true statement. I could plug in any number possible and this would be a true statement. It's called an identity. An equation that is not true for any value of x is called inconsistent. It's called an inconsistent solution. So an example of this would be something like 2x equals 2x plus 3. There's no value of x that I can plug in on either side and get this to be a true statement, because on the left hand side I will have just the 2 doubled, or sorry, the x value doubled, and on the right hand side will be doubled, and then I would have to add 3. There's no number that I can put in here that would make this a true statement. Now if I tried to solve this and subtract 2x from both sides, I'd get 0 equals 3. This is a false statement. So when I'm working and I get to something that's a false statement, that tells me that that's inconsistent. Now along those same lines, I'm going to scoot back here and leave a little extra room. If I tried to simplify this expression, I'd have 3x plus 2 equals 3x plus 2. I'd subtract 3x from both sides, and I get 2 equals 2, which is a true statement. So when I get this true statement while I'm working, like 2 equals 2 or 0 equals 0 or 2x equals 2x, that tells me that I'm working with an identity. So we've talked about an identity, we've talked about an inconsistent equation or an inconsistent solution, and then our last one, an equation that is only true for certain values of x is called a conditional equation. Now we run into conditional equations a lot. For instance, we could have something like 3x equal 2x plus 4. So when I go through and solve this and subtract the 2x from both sides, I get x equal 4. So this is conditional based on the fact that it's only true when x is 4. So these are some of the cases that we can come across when we're working with solving these. Now another nice thing about solving rational equations is a lot of times you can graph these on your calculator to kind of get a visual to see what's going on with these. And we'll be doing that with most of them. So go ahead and grab out your calculators. So we're not asked to simplify, we're asked to solve. So x plus 6 over 5 equals 2 minus the quantity x plus 5 over 2. Now this minus sign distributes to everything after it. Now if we were to graph this, we would have to make sure it's set equal to 0. So I'd have the x plus 6 over 5. I'd have to subtract the 2 across, and then I would have to add the x plus 5 over 2 and get this set equal to 0, and that's what I would graph. So let's go ahead and graph this. Now we have to be careful that we have the x plus 6 in parentheses. So I have x plus 6 over 5. And remember, we subtracted over that 2. And then we added over, we need to have this in parentheses as well, x plus 5, close parenthesis, divided by 2. So we're going to graph this. We may need to adjust our window but we're trying to figure out, does this cross the x-axis to give me a solution? And if it does cross the x-axis, what value is that? Where is it undefined? Well, it looks like to me this is a nice line. I'm going to change my window a little bit here. Instead of negative 40 to positive 40, I'm going to go negative 5 to 5. Let's have a look. And hopefully this will help me see where it crosses a little better. It looks like it crosses between a negative 2 and a negative 3. So that's good to know. It looks like I have one solution, and that solution is between a negative 2 and a negative 3. Now if I want to know for sure what that is, I could go look at my table, but again, my table is not going to give me a decimal value. It usually only gives me integer solutions depending on how I have it set up, but integer solutions are usually what I can expect. So we could do second table, and I should be able to find what's going on between negative 2 and negative 3. Now between negative 2 and negative 3, notice I switch from negative to positive on the y-axis, so that tells me I cross somewhere between negative 3 and negative 2. So to find that exact value, I go second calc. I choose value number 2 to find the 0 of my function. Now left bound I could arrow over if I wanted, or I could just put in a negative 3. And then my right bound would be a negative 2, or I could arrow over. But see how I'm covering either side, and then my guess I can just leave at my last value. And I get my 0 to be a negative 2.428571. So when I get all done with my problem here, I should be able to double check what I get for my answer, and as a decimal approximation, it should match what we just found using the 0 function on our calculators. Okay, so I know my solution is right about there, and to be very specific about it, that value is actually the negative 2.428571. Okay, so let's come up here and let's look at what we have. Now notice there are no restrictions, because I have no variables in the denominator. This denominator cannot equal 0 because my denominator is 5, and 5 cannot equal 0, and 2 cannot equal 0 either. I have no variables. There's no x's that I need to worry about. So I need to solve this. So I have x plus 6 over 5 equals 2 minus the quantity x plus 5 over 2. Well, I'd like to clear my fraction, so I'm going to multiply both sides through by the common denominator of 10. Now when I multiply both sides through, that means I actually multiply every single term through by 10. Now the reason we choose this is so the denominators disappear. So over here 2 goes into 10 5 times, so I have minus 5 times the quantity x plus 5. So now my denominators are gone. I'll distribute the 2, so I have 2x plus 12 equals 20. Now the negative 5 has to distribute. Over here just the 2 distributed. Now I need to distribute not only the 5, but take the negative with it. So I have a negative 5x minus 25. Next step would be to combine like terms. So I have 20 minus 25, which is a negative 5 minus 5x. I'm going to add my variables to the left. So I have 7x plus 12 equals negative 5. Move my constants to the right. I get 7x equals negative 17. And divide both sides through by 7. And I get x equal negative 17 over 7. Now, when you enter your answer in my math lab, this is what it wants for an answer, is this exact fraction. Negative 17 over 7. But we need to figure out if negative 17 over 7 matches what we got for a solution. So let's go ahead and jump back into our calculator. Let's do second quit to get back to our home screen. And let's take negative 17 divided by 7. And that number looks very familiar. That is our solution that we just double checked on with our graph to see where we crossed. And so this is a way for me to verify our answer. So like on a quiz, if you're not sure of an answer, this is a good way to double check it before you enter it. And on a test, you'll definitely want to do this. So I have verified that this is my correct solution as well. These are the same value. So a lot goes into these, but I would recommend always graphing these first, and when you graph them first, you're going to not have to worry about like how many solutions do I have, how many restrictions have been violated, etc. Now the problem we just did not have any domain restrictions. Let's go ahead and look at a problem that does have a domain restriction. So for this problem, let's go ahead and take a look at a rational equation. So we'll have an equal sign involved here. We'll probably also have some domain restrictions that we have to watch out for. And then we'll also have to compare those domain restrictions against our solution after we find that common denominator and solve. So first of all, to get started, I would like to graph this. When we graph something to begin with, it kind of gives us an idea of how many solutions we're looking for. So I need to get everything over to the left-hand side, set it equal to 0. So I'll be subtracting over the 7 over the x squared plus 3x minus 10. So this is equal to 0. So let's go ahead and graph this to begin with. We have to be careful about how we input this into our calculators. So we need 1 divided by, and this needs to be in parentheses, x minus 2, because we need to make sure that we're dividing through by that entire denominator, minus 4 divided by, in parentheses we need that denominator x plus 5, close parenthesis. Now again we had to subtract over, so we have minus 7 divided by, and then in parentheses we have the x squared plus 3x minus 10. So x squared plus 3x minus 10, close parenthesis. So we've moved everything across. We're probably going to have to change our graph just a little bit to see what's going on. But again, we're looking for our solutions. Okay, and so let's blow up the graph just a little bit. We can't see a lot of what's going on here. Let's switch this from negative 50 to positive 50 on the x. I don't care about the y's so much. I just want to see where it's crossing the x-axis. I don't even know if it is. It kind of looks like to me it's getting closer and closer but not quite crossing. So that's what we have here, is we have this asymptotic line where I get closer and closer to the x-axis on the left and on the right, and I never cross. So it looks like to me, just by glancing at this, that we have no solution, because I don't see any spot where it's crossing. Now another way that I could check this is I could look at the table, and remember, solutions occur where my y values switch from positive to negative, because that means it's crossing the x-axis. So let's go ahead and look at our second table values. And if we note here, I have quite a bit going on, but all of my y values are negative. I have these errors, and then it switches off to positive. So what's happening at these errors at negative 5, and what was my other one here? Negative 5 and 2 probably. Let's go ahead and snap these into the lecture as well. There's hollow points. Now this graph doesn't show it because it doesn't know enough to show hollow points. What it's basically doing is just connecting the dots, and it skips right over the spots that we shouldn't be having a graph occur on. Okay, so if we look closer at this, at x equal negative 5, and we'll just say x equal negative 5 right here, we should have a hollow point. So at negative 5 we should have a hollow point, and at 2 we should have this hollow point. So there should be hollow points there. It just doesn't look like it because the calculator doesn't know enough to put in hollow points. It just connects the dots there. So I think from this graph there's no solution. Now these are also showing me my restrictions. So our restrictions are that x cannot equal negative 5 or 2. So the graph is actually showing us quite a bit. Those are my restrictions. Now let's go ahead and solve this by hand and see what we get for a solution there. Remember, I have 1 over x minus 2 minus 4 over x plus 5, and on the right hand side I have a positive 7 over x squared plus 3x minus 10. I'm going to go ahead and factor that x squared plus 3x minus 10 into x plus 5 times x minus 2. Now what I want to do is clear the fraction by multiplying through by the least common denominator. So I'm going to multiply every single term by x plus 5, x minus 2. X plus 5, x minus 2 on the right, x plus 5, x minus 2 on the left to both terms. Now what happens here is these cancel. The x plus 5s and the x minus 2s cancel. Here the x minus 2s cancel, and here the x plus 5s cancel. So I am left with this 1 times x plus 5 minus 4 times the quantity x minus 2 equals 7. Minus 4x plus 8. Combining my like terms, x minus 4x is a minus 3x. And then I have 5 plus 8 is 13 here, equals 7. So finishing, we'd subtract 13 from both sides. And I have minus 3x equals 7 minus 13 is minus 6. Divide both sides through by a negative 3. And it looks like I do get a solution here. I get x equal 2. This is called a potential solution. Now remember, my restrictions from up here were x cannot equal -5 or 2. Well, this value of 2 violates the restriction. That x cannot equal 2. And because my only potential solution violates the restriction, I'd have to say, therefore, there is no solution. So if you wanted to talk about the fact that there was no solution here, there's no solution, so we would call this inconsistent if it asks. So sometimes they will ask, sometimes they will not, but if there's no solution, if there's no such value that I can plug in to get a solution for this, no value that I can plug in at all, that means there is no solution and it's inconsistent. So you have to watch out for that. Now again, if I go through and I work through the problem and I get an answer, that's called conditional. If I go through and work through the problem and I get a true statement at the end, that would mean that it's true for all real values or all real numbers of x, and that's called an identity. Now the last part of this will be working through a few more of these types of equations, and some will be inconsistent, some will be conditional, and one might even be an identity. So work carefully. If you have questions about the lecture, please bring those questions to class. Stop by my office, or you're always welcome to drop in at the Math Center as well. Good luck.